All right, so let me put this thing away, if I can. Yes. So, welcome to another lecture of probability and statistics. As expected, attendance dropped half already. I hope you're doing well. It's early, it's still in the morning, so thank you for being here. So please, if you didn't register in HESIS 1 for the exercise, please do so. I saw like 86 students in the lecture, but only 50 something in the exercise. We need that so we can put you, if you pass or not the exercise, so you can actually access to the exam. Okay? So do that, and also register in Ilias. I think Ilias is working well now. If you didn't do that, because you will need to download your exercise and you have to upload your exercise and so on. And if you want to see my videos again, it's going to be there. So, having said that, let's start with today. So, today, what we're going to see, this thing, I don't like it. Where I can put it here. So, today, we continue with set theory. We finished that briefly started last week. And then we go to the definition of probability and some new, some other concepts. We define what's the Laplace probability and already touched a little bit on distribution, but just because it's a special case of distribution. And we finish with combinatory, which will be main topic for probability. You need to know that topic. So let's start. So last time we defined a few rules of sets, right? Intersection, union, and so forth. And now that it comes Komolov with three important actions that actually impact probability strongly. Basically, he said, and that was not so long ago, so we are talking about 1900. He said that let's define, let's say that we have a finite probability space, so we have an omega, right? And we were talking about omega last week, so let's say that this is the set of all the possible events that could happen, and where the empty space is not, or the empty element is not there. So you can define a function p that map this element of omega to a real number. It could be any number, okay, for now. And on the subset of any element of omega, okay? And this function will hold these properties. First, it has to be positive, so it cannot be negative, so it could be 0 or greater than 0. These are the definition of imposed in this function. For all the sets of or subset of omega, this function value and the whole set of omega has to be equal to 1. And the function, this p function applied to the sum of two subsets of omega is equal to the probability, the function applied to the union of these two subsets, and it's also equal to the summation of this function applied to each subset independently. Okay? And if and only if these subsets do not overlap. Okay? So if you have the joint subset, this function applied to this subset separately, summing together is the same as applying the function to the subset summing together. Okay, so these three actions are important because kind of set the basis of how the probability function or the probability measure will work later. Alright? So, first definition. Then this is Komolov action has some consequences, and the consequences are, of course, if the probability of the whole omega has to be equal to 1, then this function applied to the empty element has to be 0, because the function cannot be negative. Okay, it can be 0 or greater than 0, and now we know that it has to be maximum 1. Alright? Then if you think in that way, this function applied to any subset of omega has to be between 0 and 1. Okay? So simple enough, but very clear. Then the next consequence is that since it has to go from 0 to 1, the complement, this function applied to a complement of the subset A in this case is equal to 1 minus the function applied to A. Okay? So remember from last week and from your knowledge, if we have omega and we have A, the complement of omega was all of this. And if this function applied to omega has to be equal to 1, then we have our 1 here. And if we subtract the function applied to A, we have the function applied to A complement. Okay? So I guess it's simple enough for everybody to understand. The next thing is, if you have a subset included in another subset of omega, then let's say that we have a small subset here, B. The function applied to the subset A, well, sorry, it's not like this. In this case, no. In this case, is A is included in B, and everything is included in omega. So, if you have this function applied to A, the value will be always less or equal to the function applied to B. Okay? That's again because this has to go between 0 and 1. And the function applied to union, if now we have two subsets, A and B, that has an overlap, is equal to the function applied to A plus the function applied to B minus the function applied to the intersection. Okay? Because we have to subtract whatever they share. So this is going to be useful later for derivations and also for your exercise, and also because it's true. Alright? Good. And I think this is the last one. You remember from our previous lecture that we can partition, for example, A, right, in A sub I, and if the function applied to the union of this partition, it has to be equal to the function applied to the summation of all this, equal to the summation of the function applied to each individual partition. If they don't overlap, but if they overlap, it will be less. So that's why this inequality equal or less than the summation of the probability or the function applied to this subset or these partitions. So putting this all together, you can already start to imagine that this function is actually what we're going to call probability later, but it will define it as a function in general, okay, with these certain properties. And the last one is the probability of the summation of this partition is equal to the summation of the function applied to this partition if there is no overlap. That's what I said before. Okay, so if there is overlap, there's going to be less, it's going to be smaller. If it's equal, if there is no overlap, it's going to be equal. You can actually prove all the things that I have said. I'm not going to go through the proof, but I put it here if you want to check it later at home. Alright? But it's simple enough. Alright, so we have talked about set, subset, omega, and empty, but we have not shown any example, but I think it's good to always relate to the reality, or whatever you call reality, but examples of set. So, for example, when you throw a die, right, what are the outcomes that you can get from a die? You can get a number, if you use a normal die, right? You can get a 1, 2, 3, 4, 5, 6. So the whole set of possibilities, 1, 2, 3, 4, 5, 6, is your omega. And then any subset would be the ones, the two, or the one and the two, the three and the four, and so on. Okay? So this is an example of set. Another one is you have, for example, a deck of cards. If you're playing poker and you're playing, I don't know, any other game with cards, the whole set will be the whole omega will be your deck of the whole deck, and the subset would be the hearts or the diamonds or the black or the red. Okay? So then you can start asking questions about this set and subset. So let's, for the first time, and the only one here in this lecture, define probability. And for that, there's going to be two definitions of probability that usually in the literature you will find. We will just use one, but I want to show you both. So when you go to the book, if you go there, you don't get confused. So one is the probability function, and the other is the probability measure. They are pretty similar, but they have small differences. The probability function, P, and we define it here as a P low capital P, is a function that maps omega to a range of between 0 and 1. So basically what we saw before we say there is a function that maps omega to any real number. Now we are saying for the probability function, it has to map it between 0 and 1. And of course, if we map it between 0 and 1, you can already think about the previous consequences of the common law of action. You're going to follow all the others, the consequences and actions. When we talk about probability function, we're talking about the probability of each element of the set of the set omega. Okay? And an element, as we defined it last week, we define as W. Okay? We call it W. So the probability of any element of omega has to be equal or larger than 0, as we defined it in a few slides before. The probability of the whole omega is equal to 1. And if you sum all the elements of the omega and you calculate the probability, it has to be equal to 1. Okay? This is what defines the probability function P. Okay? So now we come to the probability measure. What is the difference between the probability measure and the probability function? They have the same properties, but instead of calculating instead of mapping this function omega to each element of omega to 0 and 1, it maps subset of omega to 0 and 1. Okay? And that's what we here we distinguish with capital P, right? And subset could be any. Actually, it could be one element. But let's say that it's more than one element, 2. And basically they say the probability of a subset of omega has to be between 0 and 1. The probability of the whole set of omega it has to be equal to 1. And then again, because of before, the probability of the union of partition of the subset A is less or equal than the summation of the probability of the subset A or I. If there is no intersection between them, it's going to be equal. The same thing. So we're not going to continue here defining or distinguish between probability function and probability measure, but these are the two main definitions of probability that you will find. One is regarding each element, so the probability of each element to happen will be the probability function. The probability of a subset to happen is the probability measure. Okay? Just like that. To give an example of how the probability measure works, let's say that you have this fortune wheel that you see in the TV sometimes. I don't know, maybe you don't see TV anymore. So you run the rule, right? The wheel, and you get 1, 2, or 3. And you can see that the area of 1, 2, and 3 is different. So 1 is 1/4, 2 is 1/4, and 3 is half. So you have more chances to get a 3 than the other, right? And they say that if you get a 1, you get 10 euros. If you get a 2, you get another 10 euros. If you get 3, you get 1 euro, whatever. So what would be the probability measure to get the empty? So to don't get 1, 2, or 3 is 0. So here's what you have here, right? Because you're always going to get 1, 2, or 3. The probability to get a 1 or a 2 is 1/4, right? That will be the probability function because you're talking about one element. But then you can talk about the combination, for example. The probability to get 1, 2, and 3 is 1 because it's 100% chances that you're going to get 1, 2, or 3. The probability to get 1 and 3 now becomes 1 and 2. It becomes 1/2, right? And then it's the probability measure because you're taking a subset, right? These two elements there. And then the 2 and 3 or the 1 and 3 becomes 3/4. Okay, just for you to have a grasp of what we are talking about this. This is what we're gonna start doing from now on, and you will do the exercise. So you will look at what are the possibilities that you get something over the total possibility that you have, and you will see that this defines probability in a minute. So for now on, we use probability measure as a probability. Okay? So when I talk about probability, we're going to talk the probability of subset A. So you can forget it or not. It's knowledge for you. It's just for you to don't get confused if you go to the books. Of course, there is a relationship between probability function and probability measures. And basically, the probability measure of a subset A is going to be equal to the summation of the probability function of each element of A. If that makes sense, right? And the other way around, the probability function of an element of A is the probability measure for that particular element of A. Yeah, it's as simple as that. But like I say, no worries. So for now, we call probability of A. We don't talk about probability measure or probability function. We just talk about probability of A. So far, so good, right? Nothing really blowing your mind, I guess. So it comes then Laplace, and he starts to basically try to define more, how you say that? I'm using my words today. So you can try to define more formally how probability is, right, in the concept of probability. So let's say that you throw a die, right, and you want to know what is the likelihood, not the probability. We don't talk about probability yet. The likelihood that an even result you will get, right? So taking into account that it's an honest die, right? You can get, it's the same chances to get a 1, 2, 3, 4, or 5, or 6. Then the probability to get any element of the die, so a 1, a 2, a 3, a 4, a 5, or 6, is always 1 over 6, right? You have 1/6 chances because they're all the same, all the faces of the dice have the same probability to appear when you throw the die, right? So, because we say that the probability of a subset is the same as the summation of the probability of each of the elements of the subset, we can actually see what happens when an even event happens. So it could be 1, 2, 1, 3, or 5. It's the same of probability of the probability of 1 plus the probability of 3 to happen plus the probability of 5 to happen, and you sum it together. And if you do that, it's basically like multiply 3 times 1 over 6, because each of these faces have the same probability to happen. And then at the end, you have 1/2 chances of getting an even result. So what is telling you this? It's telling you that you have to count basically what are the combination, or what is what are the possible results that you could have an uneven result over all the results that could happen. And that is what Laplace defines as a probability. So it's the probability the probability is the ratio between all the possible events that you're looking at over all the possible events that could happen. And I'm using here this operator here because if you remember from last class, this is the cardinal of a set, which means all the elements, all the summation elements of the subset. Okay? So that's what we're gonna do from now on. We're gonna do ratios of possible combinations over all the possible combinations that could happen in the event. So let's go for another example so we can start warming up. So let's say that now you throw the die 2 times. So you throw the die 1 time, you look at what number you get, and then you throw the die again, and you see what number you get again, right? And then you want to know what is the probability to get in the first row a 1, and in the second row a 3. Okay? So let's do that. So first we calculate what are the possibilities all the possibilities that could happen when you throw the dice 2 times. So you can get first a 1, and in the second throw a 1. You could get the first a 1, and the second a 2, and so on and so forth. And if you put all the combinations together, you're going to end up with a number that is 36. There is a formula for this. We will go later in the class to look at how you actually can compute this, not just putting all the combinations, because you're going to get crazy at some point. Okay? But if you do this manually, you will get 33 combinations. So there is 36 combination total possible outcomes that you could get when you throw a dice 2 times and you see what number. Check that we are talking about throwing a die, it's the same die. When you look at it, the next row is independent from the first row, right? So that's important to know. So there's nothing to do between the 2 throwing of the dice. So now we have to find the subset of omega that actually meet or that actually that is 1, that the first die is a 1 and the second die gets a 3. And basically there is only one possibility that is to happen, right? Because there is only one time that you will get a 3 and the other a 6. So the probability to get a 1 and then you get a 3 is basically 1 over 36. Using the definition of Laplace for probability. All right, as simple as that. We're gonna start getting more complicated, and the exercise will get hopefully more challenging, and the exam even more challenging. No, it's gonna be the same. That is cool. It's actually fun. So the exam is not fun at all. But when you go at home and you go, oh, this is cool. How many combinations? No, it's not. And then you start calling your friends and whatever. No, it's not like that. For sure, it's not like that. So let's say now that you go, then we throw the dice 2 times again, okay? And now we ask ourselves, what is the probability that the sum of the numbers is less than 9 or equal to 9? So you can start doing this forever, right? You can ask any question. What is the multiplication? What is the sum, the subtraction, the whatever. But let's say that we are very interested in that when you throw the dice 2 times, what is the probability that you get a number, the summation of these 2 throwing of the dice is going to be less or equal to 9. Then we start doing first. We know already that our total possibility is 36 because it's again 2 times that you throw the dice. So that is solved from before. Now we have to figure out that the sum is less than or equal to 9. One trick is we know that the probability of the subset complement is equal to 1 minus the probability of the subset A, right? That is from before. So instead of looking of all numbers less or equal to 9, we can go to the larger than 9. So equal to 10 or larger than 10. And it's easier because you have less numbers to count. That's what I do in this, basically. Okay? And I think I calculated here, I put it here. So that would be the case that you're actually counting all below 9 or equal to 9. But if you count all above 9, actually you have 1, 2, 3, 4, 5, 6. So you can get a 4 or a 6. 4 plus 6 is 10. 5 plus 5 is 10, and so on and so forth, right? So basically, the probability to get larger or equal to 10 is going to be 6 over 36. If you subtract 1 minus that, you will get the probability to get less or equal to 9. That's clear, right? Is that something that makes sense? And then you get your probability. So that's another trick for you to play with. Sometimes it makes it easier. If you want to go for all the numbers that are less or equal to 9, you're good to go. It's more time for you. It's probably what an algorithm will do in the computer. The other way around. Okay, good. So, let me just check it out. So, now I want for you to know one thing. So we're going to touch about distribution here, but distribution will be a topic or many topics of the next lectures. So what is a distribution? You probably know, I hope, because that will make things easier. It's basically how, in the case of a probability distribution, is how the probability of an event actually span over the space that you have. Okay? So there are going to be events that are more probable to happen than others, or it could happen that all the events have the same probability to happen, like in the case of the dice, right? Or flipping a coin. Then, if you plot, for example, this probability over the events, let's call it E. Sometimes, some points going to be more probability to happen, some others will have less probability to happen. And then sometimes you get something like this. You probably have seen this. This is more like a Gaussian distribution. Or if they all have the same probability, you have a flat distribution because all have the same probability to happen, like in the dice. And when this happens, what is called the Laplace distribution, because it comes related to the definition of Laplace probability. Okay? So basically in our dice, they all have the same probability to happen, which is 1/6. Okay, this is what I'm saying here. The Laplace distribution is also called the discrete uniform distribution because it's uniformly distributed. It's discrete because you have 1/6, or you have 6 events to happen. It's not continuous. Okay, we will go through distribution later. But this is basically what I want to show you. So in our dice, the probability to get a 1 is 1/6, the 2 is 1/6, and all the events will be always 1/6. So you have a flat distribution, a Laplace distribution, a discrete uniform distribution, whatever you want to call it. Okay? So this is important for you to visualize, but also to starting having a grasp on distributions. So, yes. Let's do another example. So as you can see, we will be full of examples here, and I will try always to make sense of what we're putting theoretically, even we are not doing too much theory here. So let's say that we have now a coin, and we flip the coin 3 times. Okay, so you throw it in the air, the coin comes, and if you get a head, you have a 0, and if you get a tail, you have a 1. Okay, 0, 1 will be your output. So, what are our omega now? It could be that in the first row you get a 0 or a 1, that in the second row you get a 0 or a 1, and then in the third row you get a 0 or a 1. Since every time you flip the coin has nothing to do with the previous flipping of the coin, they are independent, right? So we can actually multiply the probabilities, right? Or the combination of the probabilities. So at the end, this is what I'm saying here, the multiplication. But at the end you can get a head, and a head, or you can get a tail, a head and a head, or you get a head, and tail and head, so on and so forth, right? Again, and all the possible combinations that could happen. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8. So this particular case, when you have two outcomes, 0 and 1, fail and not fail, pass or not pass, whatever that have a binary outcome, you can actually use a formula that I explain a little bit later. That's going to be your total combinations that you could have. In this case, that you have an order is 2 to the power of the repetition that you have of this binary outcome. So in this case, it will be 2 to the 3 because you have flipped the coin 3 times. And that 2 to the 3 is 8. To make it easy so you don't have to actually put all the combinations and then count it. So our whole space there, omega space, is 8. So let's say that now we throw the coin 3 times, or we flip it, and we are interested in only the events that have at least one head and one tail. So at least have to have 1, 0, 1, 1. So then we can reduce our omega and create our subset A, where at least contain one head, also 1, 0, or 1, 1. Okay? And this is what you will get. So here you get at least 1, 1. Here you get at least 1, 1. Here you get at least 1, 1. Here you get at least 1, 0, 1, 0, and 1, 0. That's it. Nothing really crazy. Right? So, what is the probability that if you throw 3 times or you flip 3 times the coin, you will get at least 1, 1 or at least 1, 0? Then you just divide our subset A that we found before over the total combination that you could have, which is 8. And that is the probability. So 3/4 in this case. These numbers, yeah, 3/4, whatever, we don't know. But sometimes you can actually have a sense of what you expect. It's a big number or a small number, and then it's a good way to check that you're doing the right calculation. So, what is the probability of the complementary of our example 2? So, the complementary of getting at least 1 and at least 0, what will be? How we can do that? From what I just hinted a few slides ago. If I want to calculate the complementary of what example 2 was, what would you do?
1 minus the thing.
There you go. Good. So you just do that, where I get it here. And basically it's 1 minus 3/4. 1 minus 3/4 is 1/4. And or you can actually go again to the subset and see that you have non-ones or non-zeros and do 2/8. But I will do 1 minus 3/4 in this case. All right? Good. So, let's do even a little bit more challenging or more thinking about this. So what about if you continue to flip the coin until you get a 1? A 1, yeah, because it's a tail. And then you stop. So what will be your probability in this case? You flip it, 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 you don't get it, you don't get it, you don't get it, or you get it at the first chance or whatever, right? So again, you can get it in the first flip on the coin, you can get it in the second, in the third, in the fourth, in the fifth, in the infinite. Hopefully not. At some point you get the 1. But it could be a possibility, right? So it could happen that you are so bad luck that you are here forever and you don't get the 1 and then you get pissed. So how do you define the probability? Because you have to do it in some way. So you have to calculate the probability to get it in the first flip, the probability to get it in the second flip, the probability to get it in the third, and sum it all together. So if you start to do this, the probability to get it in the first flip is actually 50-50. It's 1/2, right? So 1/2 of the chances we have one flip. The probability to get it in the second now is 1/4. The probability to get it in the third is going to be 1/8. And if you continue this deduction, you see that actually is like saying 2 to the -1, 2 to the -2, 2 to the -3. And if you have some mathematical background, you can already see as a series, right? And then basically it's a power series, yeah, to the -I. And basically that is the probability. That's how you can define it, just as a series. And I can assure you that if you don't get it in the next hour, at least in the infinite, you have 100% chances of getting a tail. Was right, a tail. So that's another way of looking at probability. So you can see that you can go from very simple example to getting more complex and then more useful probability examples. So now let's go now more to a real example. Let's say that you have a friend or you have this person in the street that has this nice game that promised you that you can earn money or you can make money by playing the game, right? Let's see if you can check before you enter the game if it's going to be an honest game or if you're going to actually lose money, right? So let's say that this guy, your friend, or the person in the street, set this game for you too. They say, we're going to toss the die, okay, a die. And then, depending on the number that you get in the die, you're going to get money or not. And to enter to the game, you have to give to the person €1. So in order to be able to play the game, you have to pay €1. But he said, if you get a 6, you get €5 plus your input. I return your input to you. If it's not a 6, you don't get anything. So it's not so bad. You have, I don't know, chances of getting €5 by just giving 1, and at the end you will lose €1 if you don't get the 6. So, but let's see how the average return for you will be. That means if you play many times this game, at the end if you're gonna lose or you earn money, which is what you want to do. Because once you pay €1 and you don't get it, I'm gonna have another €1 and you get it until you get 5. After 6 times you play it, it's not so fun. So let's see. How you can calculate the average return? You have to calculate the probability to get a 6 times what you will be times the return, so times the €5, right? That you get if you get a 6, minus the probability of not getting a 6. Multiply by your €1 that you give it to the person, the input, right? And if you do this calculation, you actually end up with 0. So that means that in average, you can play many times and you're probably going to be balanced when you earn and when you win and when you lose on money. So actually your friend or the people in the street maybe was not so bad. And I don't know what he is or she is doing, but you at least not going to play, you're not going to lose money. Okay? So we can say that it's a fair game. What happens when you go to the casino? Well, that's a nice story. I don't have to really tell you that it's not a good idea to go to the casino, but if you happen to have an addiction for some reason, some people have to alcohol, to other things, some people like to play, or gambling, then I tell you that it's not a good idea, but I try to convince you with probability and numbers. So let's say that you play the roulette in the casino. I think everybody knows how the roulette works, but basically you have this board where you have a set of numbers, and the numbers are divided in colors, so red and black, and there is one number, the 0, that is green. So you have 3 colors actually. And let's say that you play the easiest way to play the roulette, because it can be quite complex, and actually you don't know all the rules. but I know that you have to place your chips, right, in a color, and then the roulette, which is, is a rule that will have a ball that when you spin the wheel, the ball will at the end hit one of the numbers with the colors that are in the ball, right? That's the random thing. And if you get the color, if you get the color that you were actually putting in, you get some money. If you happen to not have that color, then you lose the chips that you put there. Okay? So that is how the roulette kind of works in the simple way. And let's say that you have to give 100 euros to have one chip, to have one chances of put this chip in the ball, so such that you will see what happens. And if you actually get that color when you spin the wheel, then you get 103 euros plus your input. Okay, so you can see that already we are talking about more money, but this is just an example. But already the earning of this is not too much, so you're going to earn 3 euros per time that you play. But if you think 50-50 chances of getting a red or a black, and well, you have the zero that you never think is going to happen, and then screw your whole play because you get the zero. But the chances are good that you're going to, well, at least, yeah, you can do wishing, thinking that this will happen. But let's do math and let's calculate, and let's imagine that we are in the casino with our paper and a pen, and we can actually calculate before we play if this is a good idea or not. So again, we have to calculate the probability to get a red times what you're gonna get if you get a red. So let's say that you put the chip in the red. You could have, say, black here. But let's say that we put the chip in the red. Then what is the probability to get a red times the return that you will get, and the probability to not get a red, and the input that you're gonna lose. And if you subtract together, you see if the game is fair or not. So, how you calculate the probability of red? Well, you have 36 spots. You have 36 numbers. 18 will be black, and 18 will be red. So 18 is our subset A. And then you have all the outcome possibilities are 37, because you have 18 plus the 0, that is a green, so it's 37. So 18 over 36 over 37 is your probability to get a red, times 103 euros that you would need if you hit there. Now, what is the probability of not getting a red? So you have the 18s that are black, plus again our green. Okay, so we have 19 now possibilities, over 37 again, because it's our whole omega. You can see that 18 and 19, they are not so much different, but when you play the number and you do the math here, you actually end up with a negative average return. That means that if you play, at the end you will be losing money. So it's not recommended to continue playing. Maybe the good option would be there, go there, play. If you win, just go and don't do it again, because you're probably going to lose that money that you put there. Nothing new, right? In average, if you were playing with these numbers, you would be losing 1.2 euros per round. Yeah, so not a good idea. 1.2 euros now do not mean too much with the inflation, but still you can buy something, I think, at least, I don't know, a croissant or pretzel, whatever. All right, so finish the part of the Laplacian probability, how you actually calculate that. I hope this is clear. I don't see faces that are so ugly, so I think if you have it in your mind what it's called, and probably you have seen this before. We switch to another topic, but it's called the odds. The odds is another concept that is useful for comparison. So mainly for comparison. So to compare probabilities, if you want to put it like that. So let's say that you have a subset A, and you want to calculate the odd of A. And basically what it does is the ratio of the probability A over the probability of not A. So the odd of A will be the probability of this, it will be the ratio of this event to happen over the probability that this event will not happen. Okay? That could be useful, for example, I don't know, if you had to decide something, if you decide to cross on red light in your traffic light, which I hope you don't do it, you can calculate probability, what is the probability to get hit and not to be hit. If it's not too much chance, maybe you can go, maybe you don't go. That's an Argentina would do, probably a German would not do that. And I hope we learn at some point about that. So for example, to decide things, what is the probability to happen? Well, you make a balance, you know, it's like how much you're gonna earn, or how much you're gonna win or not. So this is called the odds of the probability. Then you have the ratio odds, which is even maybe more abstract, but it's basically the ratio of odds. Basically, it's what the probability, no, what is the ratio of the odds of A over the odds of B. And I'll give you an example in a few minutes so you can get it better. So basically, it's the ratio between the probability of A to happen over the probability of A not to happen over the probability of B to happen over the probability of B not to happen. And this ratio is actually interesting because it can be useful. And I'll give you an example in a few minutes on the ratio. But first, an example of the odds. So let's say that you toss a 6. Yeah. Let me just see what, yeah, exactly. So let's say that we want to calculate the odds of tossing a 6, right? In the game of Ludo or in any throwing of the dice. So first you have to calculate the probability of A to happen, 1/6. I think we are all clear. That is going to be 1/6. Then the probability to A the A to not happen or the 6 to not happen is 1 minus 1/6, right? Again, because it's the complement. 1 minus the probability of 6. So it's 5/6. Then if you calculate the odds, it's just the ratio between the probability of getting a 6 over the probability of not getting a 6. Fair enough, right? So what will be the ratio of the odds of tossing a 6 versus the odds to toss a 1 or a 2? That gets a little more complicated, right? So A now is going to be 6, or and B will be 1 or 2. So the probability to get a 6, we already saw it, is 1/6. The probability to not get a 6, we already saw it, is 5/6. So the odds of this is actually 2, it's going to be the ratio. Now the probability to get a 1 or a 2, you have two possibilities, so it's 2/6. And 1 minus that probability, it gives you 4/6. And now you can calculate the ratio between them, so you calculate first the odds of having 1 or a 2. So it's the probability of having 1 or a 2 over 1 minus the probability of getting 1 or 2, right? And the other odds we have calculated before, we say that it's 1/5, and then if we do the ratio, then you get the ratio of the odds, which is 2/5. I know that at this point you will give 0 cents about this, but let me show you something that is interesting. I like this example. It's kind of old, but I really like it. So let's say that you are in USA, and you want to move to Germany, and you don't know what to do because you don't know anything about Germany. Or you are from Germany, and you want to move to the US, and you don't know anything about US. But one thing that you know how many people are killed in each of the countries. Murder, just for any reason. Robbery, terrorism, whatever you want to call it. And you go to the official website of the government of the USA and the government of Germany, and they say that in 2017, 17,284 people were murdered in the US, At that point, there was a population of 325 million people living in the US. Then you see in Germany, 405 people have been murdered, with a population of 82 million. So, yeah, it's hard to grasp. If you go to that, you say, well, yeah, they have more people, more chances to be dead, I guess. But you don't really know. You could do a ratio there, but it's not so straightforward. So then we can use our probability and use our odds, right? And then we can calculate what is probability to be murdered in the USA, right? And the probability is basically how many people were murdered over the total population of the US, and that is what we get there. And then what is the probability of not being murdered? That would be the total population minus the people that were killed over the total population, right? That's what we see here. And then you can make the same thing for Germany. So we're assuming here A is USA, B is Germany. And then for Germany, 400 people were killed over the total population of Germany. And then 1 minus that, it would be the total population of Germany minus the murder over the total population. So that's what we have now, how is the probability to be killed and not killed in both countries. Now we do the ratio, the odds of USA, the odds to be murdered is going to be the probability to be murdered over the probability to not be murdered. And that is a number that is 5.318 to the minus 5, 10 to the minus 5. So chances are, and this is a not nice statistics because this is the whole country. Of course, there are going to be cities that are more dangerous than the other cities, and within the city will be neighbors that you don't want to go, and so on and so on. But it's in general, let's say. So you have a low ratio of people being dead to the total population. And if you do the same for Germany, you get 4.939, 10 to the minus 6, right? So you already can see that there is one order of magnitude less people murdered here in Germany than US, but to make it even more consistent and more easy to grasp, let's make the ratio of the odds now becomes the number a little bit more relevant. And if you divide the odds of the USA over the odds of the Germany, you get 10.77. So you have 10.77 more chances of being killed or murdered in the US than in Germany. Then I go to Germany. No, it's not like that, but it could be, should I take this class? Well, what are the chances to pass the exam to this class? Well, we make the ratio and you see all the people have been passing the exam over the total people have taken the exam and so on and so forth. You could make decisions with this. It sounds unrealistic, but it's actually something that you can do in your real life. You could make, when you do this list of pros and cons of decision, big decision that you would make in your life, actually using the odds, it might not be so bad idea. I hope I put it that clear. Good. Finally, last thing of today is combinatory. And this is going to be one of the last, I think, basic topics of probability statistics because it's useful for all your exercise that you will use. When we say what are the number of possibilities that could happen, or for this subset of possibility, you are always going to be calculating a combination, right? And for calculating the probability, then you need to know how combination works. Because that's what you're going to do when you do Laplace probability, right? So you're always going to look at the number of events to happen over all the possible combinations. And there are two things, roughly speaking, that you have to consider. One is this event happening in an order, so it's the order of the elements that you're going to be looking at is important. And that is the first thing here. And if you take one element from the subset of the omega, if you can replace them, or once you take it, you cannot put it back. So these are two things, basic things that you need to consider. And for that, you have many options. And I want to divide these 3 in 2 options. Basically, in general, for calculating probability, you have 2 scenarios. One that you have to pick something from a subset, and the other that you have to rearrange the element of the subset. Okay? It's a different story. One thing is to pick something from the box, and you get it, or throw in a dice and you see it. The other is to rearrange things of elements of a subset. Okay? One thing is called a permutation usually, and the other is called a combination or a variation, depending on the things. So if you go to the side of rearranging elements, you have to ask the question: are the elements unique, or are the elements actually not unique? If an example of being unique is, for example, you throw the die and you have a 1, 2, 3, 4, 5, 6. They're all unique. There is no way that all are different. Other example of not unique would be colors. So it could be that 2 elements are blue and 2 elements are red and 1 element is green. So they are not unique. They share some properties. Okay? So depending if they are unique or not, they will call it with repetition, without repetition, or with repetition. And depending on that, and I'm not going to go exhaustive about how you get these numbers. I will do a few slides at the end, but not too much. You will have a formula for you to help you to calculate this in an easy way. I will not use this formula like monkeys, just using the number, but I will try to understand why these formulas are. I don't ask you that in the exam, but for you will be better because using your brain is always better. So depending on that, you will have n factorial or n factorial divided by the factorial of each of the elements, or the numbers of the elements. You can see here that this is because they are not unique. Okay? So, if you go to the left, then picking elements from a subset, then again, one question is, are the order important? So, is the order how you are picking is important, or you can pick it from any order at all? And again, can you replace it once you have picked one? Can you put it back, or you cannot put it back anymore? Depending on that, you will have 4 different ways of calculating the combination. And I'm not sure how the exam will be, but pretty sure I don't like people to memorize things, so you will get practice with the exercise and you will see how you use it. We'll talk about the exam later. I don't want to make the exam the goal of this class because I want you to... I assume that here everybody knows that you're privileged to be here to study and to have a career, hopefully, in your life. So I hope that everybody here is for learning and to use this information that I give it to you for free, at least myself for free, for the better, right? But if you're thinking about the exam and only the exam, you will have the script in the most important part of the exam, so you will have this information. There's going to be a part of, we will talk about the exam at the end of the lecture, but in the semester, but there's going to be a part of the exam that is not with the script, and one part of the exam that is with the script. And when we use these things, you will have information with you, but I would strongly recommend that you actually go and check this formula and see if it makes sense. For that, I prepared quickly 2 or 3 examples, and that's it for today. So let's see that we say order is sample with replacement. Okay, so the order is important, and there is a replacement. So once you took an element from the set, you actually can replace it. And then let's say that we have a set of elements from omega, and this every time if you have n elements from omega and k is the number of times that you have actually picked it from there, then you have k times n elements. So you have picked n elements k times, and then it's basically, if you do this multiplication, you get n to the k. This is what we saw before with the number 8 for flipping the coin. Coin was 1 or 2, right? And 3 was the number k, like here. Let's say now that we consider order important, but replacement is not possible anymore. Then every time you take one element from the n, you have to subtract it. So the first time you pick it 1, but all the elements were there. The next time that you do it, there's going to be n minus 1 element, because you cannot replace it. And if you do it again, you end up with the formula that's here, n factorial over n minus k factorial. Okay? And I think there is one more here that I put it here, that's unordered. So order is not important, and replacement is not possible. Then it gets a little bit more complicated because you cannot replace it, so you have to subtract 1 to each of the elements. And the order is not important, so you have to have all the combinations that you have. You can actually pick it from them. And then you get to this formula that you may have seen, which is called the binomial coefficient or the binomial formula. And this will be important for the binomial distribution when we go there in a few weeks. Okay? And it's called sometimes the way of choosing k from a set of n values. This is a symbol that you will see often later. Okay, so an example of this, and no more than an example that we have seen before. I think everybody knows what a lottery is, or a lotto in Germany is. So basically, you have a lady that is moving this whole ball. The ball has 49 balls, unique balls from 1 to 49, labeled with a number, and then this, at some point, the gate will open and the ball will come out, and it's going to happen 6 times, and the lady will sing the number, and then you will have your cartoon, right? And then you will probably, hopefully you have marked the number that will be appearing randomly from this ball, right? That's the lottery. And if you are lucky to get 6 out of them, you are a millionaire, right? But there is also a nice combination. If you get 1 and 2 or 3 and whatever, because if not, people will not play. So what is this? This is a good example of an order, because the order that the number appears would not matter, because if it would matter, it would be impossible to win this game, because if you got to guess the 6th number and also the order that it would appear, you can think that this would never be possible. So the order does not matter, and there is no replacement, because once one ball has appeared from the big ball, it will not happen again. So you cannot go back to the ball, okay, once you get one from the lottery. So basically, the numbers are from, the elements of omega go from 1 to 49, okay? And then the number of possible, what is the number of possible combinations? That you get 6 numbers, particular number from 49 that you have in the big ball. Then you use the binomial distribution, the binomial, coefficient, because you have unordered and without replacement, right? So n in our case is 49, and k in our case is 6. So this is the total combination that you will have. So you can already see that it's hard to win this, right? Because there are so many possible combinations to draw 6 out of 49. And one of those combinations is yours. So forget it. So what is the probability to get the lucky 6? Is 1 over this big number, and of course it's a very small number, to the minus 8. So nothing new here, but good for you to check this number. Would this make sense when you do the exercise or the exam, or your life? Even more important, you make a decision. It makes sense that it's a very small number. Yeah, it is because you have to pick 6 out of 49 randomly. Yeah, it has to be a low chance. You don't know exactly the number, but it has to be something to minus 6 at least, right? -8 is already very low. So the last slide for today, general matrix here for choose with replacement, choose without replacement, order and order, what formula you use. Again, this is for you for a quick, when you are stressed in the exam and you don't know, oh, how was it, coach, just make one of these post-it to this slide. I will give you the script at some point, and then you will have, yeah, here is the table for checking this out quickly. But that's an example. All right, I think with this, yeah, we are done. Any question in general, any question in particular, we are good. All right, so thank you then, and I'll see you next week.